All right, we're going to take a look in video number 2 here and kind of work our way through doing some buffer calculations with the Henderson-Hasselbalch equation. And we first start off by rewriting it. We just see that pH is equal to pKa plus the log of this ratio, this quantity A minus divided by HA. So that's the salt or the base, I guess would be another way of saying it, divided by the acid concentration. So part M says a certain buffer contains 1 molar acetic acid and 1 molar sodium acetate. Use the Henderson-Hasselbalch equation to calculate the pH of this solution. So we write the Henderson-Hasselbalch and we just plug in the numbers. The negative logarithm of 1.8 times 10 to the minus 5th plus the log of the salt concentration, which is 1.0 molar, divided by the acid concentration, 1.0 molar, and we see it's 4.75. Now, part N, if a buffer solution contains equimolar quantities of a weak acid and its conjugate base, then the pH of the buffer solution is just the pKa of the weak acid, because you can see inside the log term that ratio is 1, and the logarithm of 1 is 0, so that doesn't change the value of the pKa. All right, item O says to make a prediction about the pH values of each of the following buffer solutions, and then use the Henderson-Hasselbalch equation to calculate the pH. So we take a look at this first one. We have 1 molar acid and 0.8 molar sodium acetate. So when we look at the Henderson-Hasselbalch equation, we can see that our numerator is slightly smaller than our denominator. So that means that we would expect the pH to be lower. And in fact, when we calculate the pH with the Henderson-Hasselbalch, we get 4.64. The second problem asks the question the other way around. It asks us, well, if my acetic acid is smaller, but my sodium acetate is larger, then of course it's going to be the other way around. We would expect it to be higher, and in fact it is when we use the Henderson-Hasselbalch. All right, item P. A certain buffer solution contains a mixture of ammonia and ammonium chloride, which we recognize as a buffer because it's a weak base, and the salt of a weak base. And the pH of this solution is 9.43. First item, calculate the pKa of the ammonium ion. Well, the pKa is just going to be the negative logarithm of this Ka, which would be 9.25. Item 2 says the pH of this solution is 9.43. Well, obviously that's greater than the pKa. Therefore, this solution must contain more base than acid. And item 3, the concentration of NH4 plus in this solution is 0.8 molar. Use the HH, or the Henderson-Hasselbalch equation, to calculate the concentration of ammonia. Now, this may look a little convoluted, but it's not really. We write our Henderson-Hasselbalch, and instead of writing A minus over HA, I could really just write it as base over acid. And I'm trying to solve for the concentration of the base. So moving left to right across the top line, we can see that I have, I've put in all the things that I don't know, and going down to the second line, 9.25 plus the logarithm of the concentration of the base divided by 0.8, which would be the concentration of ammonium hydroxide. I get 9.43, and I can rearrange this to solve for the base, and I get 1.21 molar. All right, item Q is talking about the buffer capacity. The buffer capacity is how much acid or base the buffer can neutralize before the pH of the buffer starts to change a lot. And the pH range of any buffer is the range over which this buffer can act effectively. And most of the time, this works best when the concentrations are roughly the same. And really what we're going to say is when we have the pKa plus or minus a value of 1. So this ratio of acid or base has to be no greater than a factor of 10. Because if I take the logarithm of 10, I'm going to get positive 1. If I take the logarithm of 1/10, I'm going to get minus 1. This allows our buffer solution to work pretty well. When our range is outside this factor of 10, the buffer doesn't work too well anymore because I've added so much acid or so much base that the buffer can't effectively control the pH anymore. All right, item R asks us to look at these two buffer solutions, buffer A and buffer B. And we want to look at this. The pH of buffer A is going to be equal to the pH of buffer B. And we can see that because even though the concentrations are different, the ratio of the concentrations is the same. So it's not going to be any different than the pKa. But buffer A has got a greater buffer capacity than buffer B because it just contains more moles of acetic acid and acetate ion. Therefore, it can absorb a greater change or greater deviation from the initial concentration. Item T asks us to compute which one of these acids would be more suitable to use for making a buffer solution at a pH of 9. And it gives us two choices. One is hydrocyanic acid and one is hydrofluoric acid. And we can take a look at our Kas and go, well, wait a minute. If I take the pKa of each of these, I can see that, in fact, the first one is going to be much better for making a buffer solution at a pH of about 9 because the pKa is much closer to a value of 9. What other substance do I need? Well, I'm going to need some salt of cyanate. So I need some source of cyanate ion to make this work. All right, item V says a certain buffer contains 1 molar acetic acid and 1 molar sodium acetate at this pH. The volume is 1 liter. Part 1 of this says suppose that 1 milliliter of 10 molar sodium hydroxide is added to this buffer. Very concentrated. How many moles of OH minus ions does this quantity represent? Well, first thing we do is we're going to write our reaction. What's occurring in the buffer solution when I add this sodium hydroxide, and you can see what happens. So 0.001 liter, which would be 1 milliliter, times 10 moles per liter, which is our molarity, gives us 0.01 moles of hydroxide that's been added. Now, we're going to assume that this 1 milliliter doesn't substantially change the volume. It does slightly, but we're going to make our math easy and assume that it's still 1 liter. And after I add this sodium hydroxide to this buffer, this addition of 0.01 moles reduces our acetic acid concentration to 0.99, but raises our acetate concentration to 1.01, just a very slight shift. Now we're going to use Henderson-Hasselbalch, and when we do, we can see that our pH is only 4.75, which is very close to the original. Now, part 4 says as a comparison, what would the pH be if we added this same amount of sodium hydroxide to pure water? Well, if I added it to pure water, I would get the logarithm of 0.01, so a pOH of 2 and a pH of 12. And you can see a gigantic difference in the pH when I add this small amount of sodium hydroxide to pure water instead of adding it to a buffer solution. Right, item W, a certain buffer contains 1 molar CH3COOH, our acetic acid, and 1 molar sodium acetate. Again, we have the same situation, only now we're adding the opposite. We're adding concentrated strong acid rather than concentrated strong base. First thing we have to do is write the reaction, and you can see the H plus reacts with the acetate to form acetic acid. And again, we have the same 0.01 moles of acid that has been added. Now, after I do this, this is going to raise my concentration of acid by 0.01 molar and reduce the concentration of acetate by the same 0.01 molar. And if I plug this into Henderson-Hasselbalch, I see that my pH is now 4.73. Again, a very small change in the pH of the buffer solution. And again, we're going to calculate what would be my change to the pH if I added this to pure water. Well, for the same reasons and using the same calculations, here I've got 0.01 molar H plus, so my pH is the negative logarithm of 0.01, so my pH becomes 2. Again, a whopping huge change in the pH by adding this concentrated acid to pure water. So, without a buffer, the pH change is huge even for small quantities, but with a buffer, the pH change is almost negligible. Almost. All right, we're going to stop here before I start doing the next section on acid-base titrations.